So this is the rigid motions page of the midterm review. So we'll start with number 1, which I know some of you did a few on every page the other day, so you did some of these questions, but does not have a line of symmetry. I can fold C that way or that way and have it line up. I can fold D that way and it will line up. I can fold a circle any way through the center, it doesn't matter. There's an infinite number of lines of symmetry, but there's no way to fold that. It won't line up. Even if you think it might be diagonal, it's not true because a 90-degree turn would put that corner over there. So this one does not have a line of symmetry. Number 2, what letter has vertical but not horizontal line symmetry? So which one can be cut this way but not the other way? Can't be X because it goes both ways. It can't be B because it goes this way and not the other way. S has none. M is the only letter in that list that can be folded with a vertical line but not any other line. Which shape has the greatest number of lines of symmetry? Greatest number of these 4 would be a square. You can almost refer to question 1 where a square could be cut this way, perfectly diagonal in both diagonal directions. A rectangle is a little bit less because it can only go this way and this way. The diagonals won't line up. A parallelogram has none, and a rhombus can only be cut in the 2 diagonal directions. So square is the most. What figure does not have rotational symmetry? Which means if you turn it upside down, which one will not look the same? A rectangle will look the same upside down. An equilateral triangle, not upside down, but if you turn it 60 degrees, will look the same. Every 60 degrees it will look the same. And a hexagon, even less than that, every 30 degrees it will look the same. But a trapezoid, there's no other way that will look the same until you get all the way around to the beginning again. So trapezoids do not have rotational symmetry. Number 5, what's not an isometry? Again, this is the question we've seen all year. A dilation, because it does not keep the same size. Number 6, which does not preserve orientation. Now remember, orientation is when you name a shape around in a circular fashion. So A, B, C, D. That's orientation. When you reflect something, the orientation changes and goes the other way. So rotations do not preserve orientation. Number 7, what sequence of transformations will map ABC, this smaller triangle, onto A prime, B prime, C prime? So you can even tell without looking at the choices that 2 things have to happen. Number 1, this has to be rotated some amount that way to get A over near A prime and to get B down here and to get C over here. So it has to be rotated, but obviously it's too small. So once you rotate it, it would have to be dilated. So a rotation and a dilation is choice D. Number 8. Describe a sequence of transformations that will map ABC onto DEF. So this one you have to do on your own. Here's ABC. You could do this with patty paper. There's a lot of different ways you could do this. You could translate, and this is a hard copy to see, but it looks like it's over 1, 2, 3, 4. You'll have to answer that on your own. I know your graph paper is much clearer than mine, but I'm assuming that that's 4, although it could be 3. I'm going to say it's a translation of 4, 0, and then a reflection over the x-axis. And if it comes second, it gets written over here, like that. If you wanted to write out the whole thing in words instead of doing that, you could say a translation over 4 up none followed by a reflection over the x-axis. And there's other ways you could do it too. You could have reflected first. There's a whole bunch of ways to do it, but if you have 2 ways that work and you're going to write it in notation form, write it backwards if there's multiple steps, or you can write it out in words if you want. Next page. Quadrilateral ABCD is graphed on the set of axes below. When ABCD is rotated 90 degrees counterclockwise, which is positive, that's positive 90 degrees, its image is A prime, B prime, C prime, D prime. Is distance preserved under this rotation? We can answer that part right away. Yes, because a rotation is a rigid motion which preserves distance. So it's got to be a yes. So it can't be anything with a no. Now it wants to know where will one of these coordinates be? Will A prime be at 6, 2, or will B prime be at negative 3, 4? So one of two things is true. Either A prime is at 6, 2, or B prime is at negative 3, 4. One of those two things is true when we rotate 90. So when I take this and rotate it, and put A here and B here. Now when I rotate this, does it make sense when I rotate 90 that A is 6, 2, or that B is negative 3, 4? You can see by rotating, B is the one that makes sense. It's going to land at negative 3, 4. A is nowhere near this area at all. So the answer is that. Number 10. Graph and label the image A prime, B prime, C prime after reflection over the line x equals 1. I remember this Regents question. This was an actual question on a Regents. The line x equals 1 is a line that cuts through the x-axis at 1, right here. So we're not reflecting over an axis, we're reflecting over that line. So B would be over 1 over another. C would be over 1 over another. A would be over 5, then you got to go over 5 more. And again, your paper, I can tell I came up a little short right here because I can't see the grid. Your paper, you can see the grid. The important part is you are reflecting over this line, x equals 1, and not the x or y axis. The line x equals 1 is actually a vertical line, 1 notch to the right. Number 11. We have rectangle ABCD and KLMN. Which rigid motion can be used to prove that one of those rectangles is mapped onto the other one perfectly, meaning it's congruent? It is a reflection over the x-axis. In other words, what's the line of symmetry? Reflection over the x-axis. Number 12. ABC and XYZ are graphed. Use the properties of rigid motions to explain why they are congruent. Well, which rigid motion maps ABC on to XYZ? If I was to use patty paper and use the origin right there, and I put my patty paper over the entire sheet, we'll pretend that's patty paper, and I did this, which is a rigid motion, everything lines up. A maps onto X, B maps onto Y, C maps onto Z. So what rigid motion did we use? How about this? A rotation about the origin mapped triangle ABC onto triangle XYZ, and rotations are rigid motions, and they preserve distance. So that's why rigid motions, in this case, proved congruence. Remember, preserve distance is a great comment to use with rigid motions to prove congruence. So that is the end of the rigid motions 2 pages. And next up, when I post the next video, will be the beginning of congruent triangles.